Welcome to the final part of the static timing analysis series. Over the last 3 videos, we have built the foundations of STA, from combinational delays to flip-flop timing and timing constraints. Today, we will cover one final concept that every FPGA and ASIC engineer should understand: clock skew. Let's dive in. Before we begin, let's quick review what we learned in the previous video. We refined our clock-to-queue model and learned that a real flip-flop has two different clock-to-queue delays. Clock-to-queue contamination delay, the earliest time the output can begin changing after the clock edge, and clock-to-queue propagation delay, the latest time the output is guaranteed to become stable. These two delays are used in the hold and setup constraints. Now let's see how the clock itself can affect those constraints. Until now, we have assumed that every flip-flop received the clock edge at exactly the same time. In real hardware, that's usually not true. The clock travels throughout wires and buffers, and different flip-flops may have different routing lengths. As a result, one flip-flop may receive the clock slightly earlier or later than another. This difference is called clock skew. Clock skew is the difference in arrival time of the same clock edge at two different flip-flops. Let's look at the different type of clock skew. Let's start with the ideal case, with no clock skew. Both the launch and the capture flip-flops receive the same clock edge at exactly the same time. This is the behavior we assumed throughout the previous videos. Unfortunately, real hardware is never perfect, so some amount of clock skew always exists. Positive clock skew occurs when the capture flip-flop receives the clock later than the launch flip-flop. That means the capture flip-flop waits a little longer before sampling the data. Because it waits longer, the data has more time to travel through the combinational logic. That's why positive skew helps set up timing. You can also see this in the setup constraint, where the skew is subtract, reducing the required clock period. However, positive skew also means the old data has less time to remain stable after the launch clock edge. So positive skew makes hold timing more difficult. In the hold equation, the skew reduces the available margin. Negative clock skew is the opposite. The capture flip-flop received the clock before the launch flip-flop. Now the capture flip-flop samples the data earlier. That gives the data less time to travel throughout the combinational logic. As a result, negative skew makes setup timing more difficult. You can see this in the setup equation, where the skew increases the required clock period. On the other hand, because the capture flip-flop samples earlier, the previous data naturally remains valid for longer. That's why negative skew helps hold timing. If you're enjoying this series so far, consider subscribing to the channel. It really helps the channel grow. So how do engineers minimize clock skew? Suppose the clock reaches flip-flop 0 in 1 nanosecond, but it reaches flip-flop 1 in 2 nanoseconds. That gives us 1 nanosecond of clock skew. One common solution is to balance the clock distribution network. The goal is to make the clock travel through paths with similar delays so that every flip-flop receives the clock at nearly the same time. In this example, we added a 1 nanosecond clock buffer to the clock path of flip-flop 0. Now both clock paths have the same total delay. As a result, the clock arrives at both flip-flops simultaneously, reducing the clock skew to 0. In practice, FPGA tools in ASIC clock tree synthesis automatically insert clock buffers and optimize the clock network to minimize skew. Let's quickly recap everything we have covered in this series. Part 1, we learned how to identify timing path and calculate propagation delay and contamination delay throughout combinational logic. Part 2, we introduced the timing characteristics of flip-flops: setup time, hold time, and clock to queue. Also, we learned how to use them to check setup and hold constraints. Part 3, we refined our timing model by splitting clock to queue into clock to queue contamination delay and clock to queue propagation delay, and saw how each one is used in STA. Part 4, finally we introduced clock skew, learned the difference between positive and negative skew, and saw how engineers minimize skew by balancing the clock network. I hope this series gave you a solid foundation in static timing analysis and made the topic a little less intimidating. Thanks for following along, and I will see you in the next series.